Dear ladies and gentlemen, welcome to the filtration workshop with the title A Digital Framework for Pleated Filter Optimization. My name is Philipp Eichheimer, and together with my colleague Medya Simian, we are responsible for the filtration business area at Math2Market. In the following 2 hours, I will give a hands-on training workshop on how to model, generate, and perform filter flow simulations in GeoDict. I hope you all downloaded the material which has been provided and have been able to connect to the machines in a provided cloud solution. The workshop is divided into 2 parts with a 50-minute break. During the break of the workshop, you may ask questions in the Microsoft Teams chat, which my colleagues will try to answer. In the provided material, I prepared a step-by-step plan on today's workshop. In case you might miss a point, have technical problems, or want to work through the workshop later, you may use these slides. In the first couple of minutes, I will give a brief introduction on the problem this workaround solves. In the following, we'll then switch to the GeoDict software and start the hands-on training. The first part starts with the import of the provided CAD structure of an oil filter in the GeoDict. Here we will go in detail through the improved GUI in GeoDict 2023. In the second part, we will set up a filter flow simulation on the prepared CAD data using the new FlowDict GUI. Starting with the third part, we take advantage of the new Pleats view and generate a cylindrical pleat structure. As in the previous part, we will also have an in-depth view at the options and capabilities. In the last part, we will resubstitute the generated pleat structure into the existing filter housing. This new feature allows us to generate various individual pleat structures for simulation without touching an additional software. Testing and manufacturing of filter elements take up significant amount of cost and time in the development process of filter makers to optimize or improve filter elements. Therefore, computer-aided design, which we call here CAD, is used by filter makers to speed up manufacturing of filters and filter elements, such as cartridges. On the other hand, modeling pleats with multi-layered materials and varying pleat counts is such a tedious design process that very few designs are manufactured and tested. Apart from that, CAD data may also be used as input for simulations that predict pressure drop, filter efficiency, and filter lifetime of filters. In this workshop, we present a digital simulation framework that starts with the CAD data, but then allows the automatic parameter studies on the pleats. Compared to other methods, our 3D image-based approach works completely automatic and requires no manual meshing steps before running the simulations. This workflow enables to save time and material in the engineering process, thus decreasing the time to market performance significantly. The diagram shown here highlights the individual steps of the workflow to optimize an existing filter element. It starts with the import of the CAD structure into GeoDict. Using PleatGeo, it is possible to generate cylindrical pleat structures with given input parameters to fit in the original CAD filter. With this feature, several structures can be saved by varying parameters such as pleat count, pleat height, or several porous layers. In the following, the parametric simulations are performed either on a workstation sequentially or in parallel using the new cloud computation capabilities shipped with GeoDict 2023. By analyzing the results, the best performing configurations can be found and tested digitally. These promising prototypes are now manufactured and validated at the test bench. This procedure allows to optimize filtration relevant parameters, saving material and time in the production and testing of filter elements. As a classical application for this framework is the optimization of pleat counts in a filter element. By running simulations with different pleat counts, it is possible to find the optimum between the pleat count, which is representative of the filter area, and pressure drop. In the plot here on the x-axis, we show the pleat count of a cylindrical filter element in the geometry. And on the y-axis, the resulting initial pressure drop. The simulations have been performed with a volumetric flow rate of 50 liters per minute and using oil as fluid. We see that the pressure drop decreases with increasing pleat count at the beginning, but observe a reverse behavior after the pleat count of 56 is reached. At this stage, the beneficial effect of increasing filter area is no longer favorable, and pleats might be tight and the initial pressure drop increases further. To produce filter elements in the minimum of this curve is the goal for a good performing filter. In the presented study, for example, only geometry with 56 or 58 pleats would be produced and taken to the test bench. As already pointed out, today we will import a given CAD structure into GeoDict. Then we will prepare the structure by assigning inlet and outlet to set up a filter flow simulation. To showcase the newest feature in Pleat View, we will generate a cylindrical pleat, which is substituted into the provided CAD data. Using this framework, it is possible to design and generate various geometries and find the best performing configuration. Now we'll start with the hands-on training. For this reason, please now open GeoDict. In some instances, it might be helpful to have the prepared slides open, maybe on a second screen, in case you miss a point or have some technical problems. For all the participants which are new to GeoDict and are not known with the software, I will give a short overview of the modules we have here and the software itself. In the menu bar on top, we have the Files tab where we can save and open structures, as well as choose the project folder. Next to it, we have the Import, where we can import structures depending on several input types, for example, viscosity, FIB-SEM, we're using the Import GeoWall, or the Import GeoCut we will use today in the workshop. Next to it, we have the Model tab, where we have our structure generator situated. Here we will use today the Process Geo module as well as the Math Geo module later on. To run simulations, we can also use analysis tools, for example here PoreDict or MathDict, but this we don't use today in the workshop. Under Predict, we find modules to predict physical properties, for example, flow rate, pressure drop, which are very prominent in the filtration business area. And for this, we have here the FlowDict, which we'll use later on to set up the complete flow simulation. Last but not least, we are also able in GeoDict to export data. We can export it as CAD structure, but also to third parties, such as Fluent or Abacus. Each time we start to work with GeoDict, we first set the path or the working directory. This can be done either when we right-click here on the path and click Select Project Folder. On the cloud, we have then the provided data. We navigate to the workshop of filtration and we click here Choose. We set the user data according to the file here and click choose. Now GeoDict sets the user path to the data, and everything which we produce in GeoDict will be saved under this path. To import CAD data, we will navigate to Import and select Import GeoCAD. Now in the module menu, we see the specifications to this module. We see that we can import STL files and OBJ files. And by clicking on Browse, we can search for these files which are provided. For this, we go one direction to the provided data, and we see a folder called Input Data CAD. Inside this data, we see the OBJ file, which we are going to use in the following. By double-clicking, GeoDict loads the data into the software. We then see a window where we can specify the inputs before we import the structure finally into the software. Beginning here, we can specify if we want to have voxels only or surface only. In our case, we want to have both, just to see the comparison. At first, we specify always the unit in the file, which in our case is meter. We then hit the suggest button and the window pops up where we can enter the voxel count, which means how many voxels will be resolved for the longest side of the geometry which is to be imported. Here we select 1000 and click OK. Now GeoDict suggests voxel lengths here. We see that the largest voxel length is in Z direction, and depending on the input of the structure, we see now here the lengths in X, Y, and Z in millimeters, as well as the voxel length, which is here 109 micrometers. In the next, we can see here on the right hand side all the meshes that have been found in the file. If we would now import the structure as is, we would end up with 10 different material IDs. To let materials look clean, we can assign here in the new GUI the material IDs to be all one material ID, for example, for solid parts. This keeps everything very clean and compact, and later on the material legend will be also very nicely when the visualization is happening. So here for all of the material IDs, we select material ID 1 in red. This can be done except for the filter media, which is set here for material ID 2. Furthermore, we also need to specify the fluid here. In our case, we want to simulate oil. So we click oil and press OK. Last but not least, we can also set already here that, for example, the filter media should be a porous media. For this, we click here under the filter media on the manual solid material selector, and we can specify here our porous solid, which is also pre-chosen by oil, as we set oil as the fluid phase. Additionally, we can enter here information about the structure. After we entered filter media in the information tab, we can click OK, and everything is correctly assigned. Then we can click on import to import the structure into the software. The import of the structure lasts around 4 minutes because each of the material IDs will be separately imported into the software. In case we have technical problems, you may also load the structure which is already implemented. For this reason, we have the provided data. So here you may go under File and then Load Structure and then navigate to the provided files and load the imported structure. After the successful import, we see that we have a warning. So GeoDict asks us if we want to load the surface triangulation, which we decline by clicking on No. And then we have an additional warning, which says that the imported meshes are not watertight. This will fix in the following steps. I will show you in the next couple of minutes how to make the meshes watertight to have a successful simulation. So we click here on OK. Now the structure is fully imported. So we see here on the left hand side, we can see the structure. So we see the voxels in X, Y and Z direction, as well as the voxel lengths which we specified. When we extend the structures tab, we see the domain size in centimeters. So this is one of the control mechanisms we have. So we see, based on the real structure, which is also around 10 centimeters large, that everything is imported successfully. Furthermore, we also see that all the changes we made to the meshes are applied. So we only have 3 material IDs instead of 12, which has been in the beginning. So we see that we have all solid parts under material ID 1. We have the filter media under material ID 2, specified as oil and porous. And we have material ID, which shows us an overlap, which we will resolve in later steps. To have a first look at the structure which we imported, we can click here on the 3D representation. And after a couple of seconds, we see the filter in 3D. So we have a first glimpse on how it looks like and how the functionalities might be. So we see on the very top here, we see the inlets, which are the small openings. And in between we see the outlet, which is the larger opening. So we know that the flow comes here, moves through the inlets, then passes from the outside to the inside through the filter media, and then discharges again in the middle through the outlet. To have a look at the filter media, we can click under structure, and then we can move the sliders for the clip in Z from the right hand side to somewhere to see the filter media, which is imported correctly. We furthermore see also specific parts as the inner netting or the spring in the inside of the structure. As the warning suggested in the beginning, the meshes are not watertight. So this means that we have a connection from the outlet of the domain to the inside. And in the complete filter simulations, we need to have an enclosed geometry, which means we now have to seal the geometry by assigning inlets and outlet phases. To do this, we go again under the two-dimensional representation. We then choose the Z direction. And by moving the slider of slice, we can slice through the whole structure. And we'll set or place the slider at the very last slice. So here we have a very good view of the inlets and the outlets again. And we now want to assign material IDs to these inlets and outlets. This can be easily done in GeoDict using the Select Voxels tab in the menu bar. By clicking on the Select Voxels, the voxel selection opens. To now set material IDs in a two-dimensional planar view, we have to specify the component mode, flood fill component plane. We then click by holding Shift in each of the inlet once. After doing so, we see under the selected voxels that we have, for each voxel we clicked in the inlets, we see a position in X, Y, and Z, as well as material ID. The flood fill component plane now floods from each of the voxels in each direction in 2D view until it reaches a different material ID, which is in our case material ID 1. To have also separation material IDs, we select as new material ID, for example, material ID 4, which is still unassigned. And we give, of course, the material information. In our case, would be inlet. And then we click on Run. We see now results that each of the inlets or each of the voxels we selected in each inlet is assigned correctly to material ID blue, which is also now displayed here in the material information with the specification of inlet. And when, for example, we set the material information with some information about inlet and outlet, GeoDict directly assumes the material ID from ID 0 oil. The same we will do now for the outlet. So we'll click once in the larger opening to select one voxel in the outlet. We again receive the X, Y, and Z coordinate as well as the material ID of the selected voxel. We leave the component mode to flood fill component plane, but we change the material ID to material ID 5. As we now have an outlet instead of an inlet, we also change the material information to outlet. Then we click Run. Now we also set the outlet of the filter. Last but not least, we want to enclose the entire outer part of the filter with some solid material. This has the benefit that we don't expect velocities to be outside of the filter media, and therefore when we assign it to solid, the software does not compute any velocity outside, and we save memory and computational time. To do so, we click somewhere outside the domain, can be in some corner, as in my case here in the right corner. We obtain again the position of the voxel we selected in X, Y, and Z, as well as the material ID. Now instead of the component mode flood fill plane, we want to fill the surrounding of the filter media also in the third dimension. So now we click on flood fill component. As a new material ID, we will set here material ID 6 and specify material information to be void. Then we click on Run. After the materials are assigned, we may switch back to the three-dimensional view to see the results. We see now that the entire filter is enclosed in a material, as well as we have set the inlets here in blue and in purple the outlet. Now in the next step, we want to resolve the overlap. For this, we have to look where the overlap happens in the structure to confirm if it's like a solid part or if it's something important which influences the flow around it. For this, we click on the color and visibility settings and we set material ID 6 to invisible. We set the inlets and outlets to invisible so that we see here the yellow phase. We then click on structure and this time slide in the Y direction to get also a cross-sectional view on the yellow phase. To see that we only have yellow here at the inlet parts. In case you should have in one of your samples several overlappings, you may set all of the material IDs to invisible to see all the overlappings. In our case, the overlappings are quite surely entirely from the material ID 1, so we don't have any complications when we reassign it to the material ID 1. For this, we make all the material ID again visible. And then we select under Model, Process Geo, which opens the Process Geo module. And then under the first tab, we click Reassign and leave Reassign Material ID as subfunction. We then hit Edit. And in the popping window, we may select the old material ID you want to set. So in our case, will be yellow, and the new material ID, which will be red. We then click on OK and on Reassign. We now see that all of the yellow overlaps are converted into the material ID 1 red. In the next step, we want to check for the materials that everything is correct and set also the permeability for the filter media. For this, we select the constituent materials here in the menu bar. We then see for each of the material IDs the corresponding constituent materials. Here, for example, to make it look smoother and more appealing, we may specify as the information here, for example, as solid parts. We leave it as solid manual and click OK. Material ID 2 is correct with oil and manual, but here we need to set a permeability. This permeability is in most cases obtained from experiments and represents the material permeability in meters square. But we can also, when for example information about the filter media is present, we can generate the filter media in GeoDict and run a flow simulation on the filter media to obtain a material permeability, which is then inserted here. In our case, we take a permeability of 1e minus 11 meters squared. Apart from that, we could also specify mechanical and thermal parameters, but in our case, it's fine to have only the permeability set. We then check for the inlets and outlets to be the same material as in the material ID 0. So in all cases, this should be the same oil. And we change for material ID 6 because we want to have it as a solid instead of a fluid. We set it to an arbitrary solid, so solid manual, and click OK. This sets also the permeability to 0 because solids don't have any permeability in our case. And then we click on Run. Now all the parameters are set for the structure. And to save the structure as is, we click under File and we click on Save Structure As. And we could give it some specific name to recall for later. In our case, I add the information that we here have a geometry with 56 pleats. And we click on Save. Now the structure is ready to set for the flow simulation. In the next step, we want to set up a flow simulation. For this, we go under the Predict tab. We click on FilterDict. And we see from the beginning that we are in the filter media regime. As we simulate a complete filter, so a filter with housing, we don't select the filter element, we select the complete filter. And then we have the sub-functions complete filter lifetime simulation, where we also involve particles. And we have the filter flow experiment, which only computes the flow through the entire filter with housing. To specify the options, we click on Edit. First of all, we always change the result file name. And mostly want to have here some information that you can later use to remember the input we had here. So in our case, we can say that we have, for example, 56 pleat in the structure. Then under the constituent materials, we again check the import of these materials. So we have the material ID 0, which is oil as fluid, which is the same for inlet and outlet. We have a porous phase, which is the filter media, as well as the solid parts and the void are in solid. And then we check under the permeability that we have set a permeability for the porous phase of 1e minus 11 meters square. Then we click under the flow experiment. Under the flow settings, by default, we have the flow motion of fast flow, so Navier-Stokes. In our case, for example, we can also click here on Stokes-Brinkmann. Specific to this very new GUI is that we have the inlet and outlet, which are selected automatically if the information is given. So for example, if somewhere in the material information the word inlet is written, GeoDict automatically assigns the material ID here in this GUI. But for example, we could also select the material ID or the inlet by ourselves. Then we can decide about the if we want to apply a pressure or a flow rate at the inlet. We also have here standard units for the complete filter simulation. So in our case, we want to have 50 liters per minute as flow rate at the inlet. The same we have at the outlet. So as we specify outlet in the material information, GeoDict automatically assumes material ID 5 to be the outlet, which is correct, but we could also specify here different material IDs. And last but not least, we can specify the domain boundary conditions. In our case, as our filter is enclosed in a solid material, we will set here no slip, because in the solid we don't have any material movement. In some of the parameters, we could also choose, for example, symmetric, which is mostly doable when, for example, you have like perfectly symmetric objects. So we can reduce the material or the size of the geometry by setting symmetric boundary conditions and then only compute 25% or half of the structure. In the next step, we directly go for the solver settings. So here in the first place, we can give a simulation stopping criterion, which we leave as default. We see the parallelization is depending on our machine, which is now 8 parallel processes. We then check that the multigrid method is activated. So we have an achieved simulation time, but a higher RAM consumption. And last but not least, we select the grid refinement to be enabled. The last tab, if you plan, for example, to publish or to show the equations which have been computed, you may use this equation sheet here, which show the equations which we compute with Stokes and Navier-Stokes, which are the momentum of conservation and mass of conservation, and also some references from the literature. We then click on OK to store the settings. And in the normal case, we would now click here in the module section on Run to start a simulation. But as the simulation in total takes around 1 hour, which is due to the workshop time limited, we pre-computed the results for you, which we then will load in the following and visualize in this sample. Before we move on to load the results and to proceed with the further steps, like the generation of the pleated structure and the resubstitution of the new pleat structure into the existing housing, we'll have a short 15-minute break to fetch a coffee or get some fresh air, and then follow up with the workshop